Dear students, welcome to the Department of Electronics DSP class. This is your 8th class. Okay, in the last class what you studied, we studied about the unit step function, units impulse function and ramp function. They are all comes under basic continuous time signal. Okay, what we studied in the last class, we studied the basic continuous time signal. In that, these three completed. In today's session, you are going to study the another three basic continuous signals. Okay, what are they means? They are the exponential signal, sinusoidal signal and the pulse signal. Okay, these are very easy. Okay, let us begin one by one. First one is what your exponential signal. All of you know the exponential form. Okay, usually e with respect e something power, if you have written, then it is called the exponential. So here also, if we have written the signal using e to the power of something, then it is called a exponential function. A real exponential signal in its most general form is written as x of t. All of we know that x of t is nothing but what? It is a continuous time signal. If we have written this x of t is equal to b into e to the power of at. This is the expression for the exponential signal. Okay. X of t is a one continuous time signal. If this is expressed as b into e to the power of at, then this is called a basic continuous exponential signal, where b and a are what? They are the real parameters. Okay. Always what happens, the parameter b is the amplitude of the signal x of t at t is equal to 0. Always what happens, b is the amplitude of the parameter at x of t at t is equal to 0. And another one important point about this exponential signal is there are the two types of the exponential signal. In that, first one is the decaying exponential signal and next one is called the growing exponential signal. If the a value is less than 0, then x of t is said to be decaying exponential signal. If a is greater than 0, then x of t is called the growing exponential signal. Okay, if you see the figure, then it is clear for you. Okay, let us revise what do you mean by the exponential signal. If the continuous time signal x of t is written as b into e to the power of a of t, then this signal is called a basic continuous time signal, where b is the amplitude of the signal at t is equal to 0. And next what happens, there are the two types of the decay exponential signals are there. They are called the decaying exponential signal and the growing exponential signal. If a is less than 0, then it is called a decaying exponential signal, and if a is greater than 0, then x of t is called a growing exponential signal. Let us see figures here. So here what happens, a is less than 0. Okay, this is what your t value and this is what your x of t value. If a is greater than 0, then what happens, t should be greater than or equal to 0. B is nothing but this is the amplitude of the signal at t is equal to 0. this amplitude of the signal is decreasing. Okay, then it is called a decaying exponential signal. What happens? X of t is decreasing from high end to the low end, then it is called a decaying exponential signal. Similarly, growing exponential is nothing but what? B is increasing. Okay, here B is nothing but what? Amplitude of the signal at t is equal to 0. If this is t is also increasing, amplitude is also increasing, then it is called a growing exponential signal. I think it is clear. Next, so fifth one is the sinusoidal signal. All of we studied the sinusoidal signals. So here in the DSP, we are showing that sinusoidal signals are always periodic. So for that, first we have to consider the continuous time signal, that is x of t is equal to a into cos of omega t plus phi. This is even standard equation for the sinusoidal, where a is what your amplitude of the signal and omega is the angular frequency that is measured in radians per second, and phi is the phase angle in radians. Let us show that this is a periodic signal. The period of the signal is defined by t is equal to 2 pi divided by omega. A continuous time sinusoid is always periodic with period t. This can be proved as follows. Consider x of t plus t is equal to a cos of omega. T is replaced with t plus t plus phi is equal to a into cos of, just you multiply inside, omega t plus phi. A cos of omega t plus this omega and capital T is nothing but what? You see here, omega t is equal to 2 pi. Okay, plus phi. This equation is equal to a cos of omega t plus pi. That is 360 plus theta. Omega t plus phi is nothing but theta. Just you see in your trigonometry what happens cos of 360 plus theta. Here theta is nothing but your omega t plus phi, that is equal to cos of theta, that is cos of omega t plus phi. A as it is, this is equal to what? Your x of t. X of t plus t is also equal to x of t, which defines the condition of the periodic signal. Therefore, continuous time sinusoidal signal is always periodic. So the sixth one is exponentially damped sinusoidal signal. Exponentially damped sinusoidal signal. So what is the definition of the damped signal and undamped signal? First, you should just remember when you are studying the oscillators. There you studied the damped and the undamped sinusoidal signals. Okay, damped is nothing but what? Here the time changes, no? The amplitude of the signal is also changes. This changes are another one, or the perfect definition is when time increasing, amplitude decreasing. This is called the definition of the damped signal. Undamped is nothing but what we are using in our lab or every practicals. That is, here you are drawing, here you are taking the time. Amplitude remains same when the time changes. That signal is called the undamped signals. Okay, but in the signals what we are studying, that is exponentially damped sinusoidal signal. The definition of this is very simple. The multiplication of a sinusoidal signal, that is, what is the equation for the sinusoidal signal? A into sine of omega t plus theta, by a real valued decaying exponential signal, that is e to the power of minus alpha t. If you multiply this decaying exponential signal with the sinusoidal signal, you are going to get the exponentially damped sinusoidal signal. Here you see results in a new signal referred to as a exponentially damped sinusoidal signal, that is as shown in below figure. Okay, very simple definition is there. Already we have studied the decaying exponential signal. Okay, that is what your e to the power of minus alpha t. If we multiply this decaying exponential signal with the sinusoidal signal, that is a into sine of omega t plus theta, the resultant signal what we are getting, that is called a exponentially damped sinusoidal signal, and this I have shown here. So here I have written the expression for the exponentially damped sinusoidal signal, that is multiplication of this and the this. Here you see, this is what your continuous time signal, that is equal to a into e to the power of minus alpha t sine of omega t plus theta, where alpha is always greater than 0, and this is the representation of the exponentially damped sinusoidal signals. And the last one is what your pulse signal. There are the two types of the pulse signals are there. They are called the rectangular pulse signals and the triangular pulse signals. So rectangular pulse can be defined as, this rectangular pulse is equal to 1 when your modulus of t is less than 0.5 and this is equal to 0. That means modulus of t is less than 0.5 equal to 0. Other than this, all the values are 0. So let us see once again, the rectangular pulse is written as RECT of t. It is represented as RECT of t, and this value is equal to 1 for modulus of t is less than 0.5. Other than this value, always this rectangular of t is equal to 0. So here you see, this is the representation of the rectangular pulse signal. Okay, this is the representation of the rectangular pulse signal. So this is what your rectangular t and this is the t signal. So here t along the x-axis, along the y-axis rectangular pulse. Always this is equal to 1. When it is equal to 1? When your t value is in between the 0.5 and the minus 0.5. For other values, RECT value is equal to 0 for other values of t. Whatever may be the t value, above the 0.5, above the plus 0.5 and above the minus 0.5, this RECT value is equal to 0. Okay, and next what happens? Always height and area should be equal to 1 and width is also equal to 1. Width is also equal to 1 and height and area is also equal to 1. So by seeing this, we can write the x of t equation is equal to rect of t minus b divided by a, where x of t represents the rectangular pulse of the width a and center at t is equal to b. Both the t and b are equal. This is what your equation for the rectangular pulse. Similarly, now we will move to the triangular pulse signal. So this is what the representation of the triangular pulse signal. It is written as TRI-T. TRI of T is equal to, how it is defined, this value is equal to 1 if modulus 1 if modulus of T, that is modulus of T is less than and equal to 1, and this value is equal to 0 elsewhere. Okay, that means for this value what happens, triangular of is equal to 1 minus modulus of T. Other than this value, this triangular of T is equal to 0. So if we have drawn this drawn this one, then how you are going to get, means here in between 1 and minus 1 you are going to get TRI of T is equal to 1. Other than these values, that means more than 1, more than minus 1, all the values of TRI equal to 0. And here also height and area is equal to 1, whereas width is equal to 2, because this one 1, width is equal to 2. So by saying this definition and this figure, we are going to write the triangular pulse is equal to, so y of t represents the triangular pulse. That triangular pulse can be written as t minus b divided by a, which describes the triangular pulse of the width 2a centered at t is equal to b. And both the pulses is nothing but our rectangular pulse and the triangular pulse exhibit the even symmetry. That means both are the same in the positive and in the negative quadrant. Both pulses exhibit the even symmetry. This is what about the continuous time signals. This is what the reference books. This is what my concern about my students. Okay, meet in the next video.